over all of my career, really, the one thing I've been always working on is, how do we deal with big data, and do we need to keep all the data? And that was one of the questions Tim asked several times. And how can we get away with not using all the data but getting all the information? And X-ray CT is a perfect kind of example of where we want to do that. And one of the reasons I titled my talk is kind of looking at low-dimensional structure in volumetric imaging. So volumetric imaging, whether it's 3D or 4D images, they're massive. We're talking billions of pixels or voxels, billions of numbers we have to store. And but a kind of a nice example I always think is, even if we just have 1,000 by 1,000 image, and each pixel just has 10 different gray values. If I count all the different images that I can represent with, just 10 numbers per pixel, but 1,000 by 1,000 image, I have 10 to the, I think it's 10 to a million different images. 10 to the million, that's, significantly more than atoms in the universe. I think, only, I don't know, 2 to the 100 or so, or it's 10 to the 100 atoms assumed in the universe. So, there are loads of images out there, but the images we're interested in are very few and far between compared to the wealth or amount of images that are out there. So if you go to MATLAB and you just say rand n 1,000, you get a random image, but it's just noise. And you can do that until you fall dead. You never get an image that's actually an image, as in terms of an image you're interested in. And the reason is really that you randomly pick one of these 10 to the million images, and most of those are not interesting. So the images we're interested in are really a very, very small part of all the images that we can ever kind of get. So there must be structure in that data. So interesting images have a lot of structure. They are not 10 to the million, in kind of complexity, if you want. So how do we capture that structure? How do we kind of encode that structure? And how do we then use that? And that's really kind of the thing I want to talk about. Now, before I start, let me just kind of say most of it isn't my work. I just gently encouraged my PhD students and postdocs to do the stuff I'm presenting here. So I just want to acknowledge, there's a lot of people's work in what I'm going to present, and I won't name them by name individually for all the kind of different things, but here's a kind of overview of the people. Now, let's kind of remind us before I talk a bit more about concrete problem about kind of the X-ray imaging. We kind of had an introduction already this morning by Tim about X-ray imaging, and X-ray imaging works by using X-rays, and and we think of X-rays as little particles often in X-ray imaging, unless we do a kind of a coherent imaging where we might want to think of them as waves. But the particle view is really quite a useful one. So we're shooting these little particles through an object, and some make it through the object and some don't make it through the object. So that's really all we're doing. And we're detecting how many we're getting through the object. And that, we do that trillions of times with trillions of different X-rays, and we then rotate the object and look at the object in different ways. And we've seen this morning, there's lots of examples out there, and if you have a nice sample where we can shine lots of X-rays through and we get lots of data and we reconstruct the image, we get really good volumetric images. So here's kind of a mathematical model of really what's happening. So to understand, the problem as we normally do it, and kind of the problem we're facing, we kind of have an intensity of X-rays. That's kind of this intensity. That's kind of the X-rays that are emitted by our source. And I labeled everything with a big E here, and the big E stands for energy. So we have X-ray energy photons. X-ray photons, and each photon carries a certain energy. And we're here looking just at photons of one energy. And then these photons interact with material, and that's kind of described by this mu function is a mass attenuation coefficient, which depends on the location you are in your object. And again, it depends on energy. So you have this kind of exponential function. You have an integral over a line. That's a line where your X-ray travels. So you assume your X-ray travels along a straight line. Some of the X-ray get lost or scattered. And you just assume you detect just the directly transmitted X-rays that don't interact with your material. And you measure basically the amount of X-rays that hit your detector. That's a basic model we use in X-ray imaging. And the reason I put that up, first of all, because like all good models that we're using, this model is an approximation. And the other thing why I put it up, it's basically a linear model. If you use that simple model, it's basically a linear model. So we can easily linearize this model by getting rid of the exponent, by rewriting our equation. And often we discretize things, and we kind of end up with a matrix vector model where we have some observations y, and each observation is basically measuring how many X-rays make it through the object along a line. And we have our image here is X, so just vectorized if you want, just taking each pixel's density or mass attenuation coefficient, putting in a long vector. And A is just the model that looked at the intersection of the X-ray beam, this one line of X-ray along which we're measuring at that point of time, with kind of a discretized representation of our image, so with each voxel. So that's the simple model. And that's where our problems already start with, even in this wrong model, because it's a linear model, which is just an approximation. We haven't talked about noise yet and all the other things, but even that problem is difficult to solve for several reasons. So it's very large. So, our image is, say, has 1 billion pixels, so 2000 by 2000 by 2000 is kind of very standard to use in X-ray tomography. Our projections, we have 2000 by 2000 on each detectors, and then we're looking at 3,000, 4,000 different angles. So again, here we're talking at billions of measurements. So A is a massive matrix. So the first question is, we never actually compute or store A. When we reconstruct things, A is just too big to be stored. So we compute it on the fly if we're using certain algorithms. So the other thing is, it's a very ill-posed problem. So X-ray tomography, if there's a bit of noise on Y, and if you try to invert it, your X just blows up. So we need to have some regularization on this problem. So typically when we reconstruct these images, and most images you see or saw today probably have been reconstructed with the filtered back projection algorithm. Now that's a very fast algorithm, basically works on projection by projection, does a bit of filtering, and it kind of smooths it back. And very fast, very efficient, works really well if we have enough data and if the data is of good enough quality. Now, if we don't have enough data and if the quality isn't good enough, we normally use iterative methods. Now, iterative methods, any optimization algorithms, it's a linear problem. We've been doing y equals ax problems for hundreds of years. But because it's so large and because it's ill-posed, it's very slow to solve. We need to regularize it and so on. So there are lots of computational problems. Just computing a times x, with a typical data set until, a few years ago, it was nigh impossible to compute on a typical lab machine, because on a synchrotron it's a bit easier, but because on a synchrotron the geometry isn't kind of this X-ray cone where you come from a point to detector. On a synchrotron, you kind of assume all your beams to be parallel, and then you can slice the problem into nice separable 2D images rather than 3D. But on the lab machine, just computing this problem is now impossible. Nowadays, with GPU and especially written GPU code, you can now solve this problem. There's still problems in getting, because you need to get Y and X typically in the RAM of your machine to effectively work it. I mean, you can save it and load it back into your machine, but there are computational problems in dealing with this sort of problem. All right. So, computational, the size in X-ray reconstruction is a big problem. So, the one first question is, how do we deal just with this data size, even if we just think of inverting a linear system? Now comes in the next set of problems. So there's noise. I don't think that's a big problem. So there's Poisson noise and there's kind of Gaussian noise, because we're talking about these X-ray photons and the interaction of them. So there's a lot of Poisson noise. But we can model Poisson noise and we can use it in optimization quite easily. I don't think that's, is the big problem. A bigger problem is, if we, for example, we have our object we want to scan, but we don't have time to scan enough projections. Or we might want to scan an object, Fabrice showed the plane, large scale. How do you take a jet fighter wing and you scan a jet fighter wing in an X-ray machine? It's difficult to rotate. It's a flat structure. So here in this video we have a little carbon fiber panel with a stringer on. Think of this as being much further extended. You can't just simply rotate it. So all you can do is you can just wave it around in front of your X-ray source and get some data. The problem is you don't get enough data for reconstructions. So how do you deal with these kind of problems? So in industry, these kind of problems occur quite a lot. X-ray CT works really well if you're imaging cylinders. If you're imaging flat objects, you need to do different things and kind of you lose information. So you need to kind of deal with that. There are lots of other physical phenomena that we've neglected so far in our model. So we haven't talked about scatter. X-rays don't just disappear when they get absorbed, they scatter. That means they just deviate from the straight and narrow. They just end up on our detector where we don't expect them. That leads to artifacts. So scatter is a big problem. Modeling it, removing it, a massive problem. And the last problem is what we call beam hardening, because the model I had earlier, which is kind of this model I have here, the only thing which I've added here is an integration over energy. Our X-ray source produces X-rays of different energies, and our material absorption depends on energy. But our detectors typically, unless we have one of those fancy ones that Tim talked about, which actually resolve energy, most detectors, they just kind of average over all the energies. So that's actually the equation that we want to use in our model, but that we can't linearize easy. If we try to linearize it like we had earlier, we have this log sum exponential function, and working with that and optimizing with that function is absolutely very difficult because of the log and the exponent. Optimization can be very slow and very difficult. Besides, now we don't have just one image, as Tim said earlier. Now we have kind of one image for each energy band, and say if we have 200 energy bands, our dimensionality has kind of blown up to 100 folds. All right, so because one of the tasks today is kind of to look at what are the big challenges in X-ray CT and what can machine learning do for us, really. So what are the kind of, if we want to do machine learning with X-ray CT data, what are the kind of the main problems that came to my mind when I thought about it? And one of the things that I always think is really important to bear in mind in X-ray imaging compared to your MNIST databases or your CFOT databases that are typically used in machine learning. X-ray imaging, you have very large data points. So you don't have just images that are 1,000 but 100 by 100, or 200 by 200. They are 2,000 by 2,000 by 2,000, and these are the small images. So you have very large data points, but you tend to have very few of them. In some application, where you have the same object, say in a production line setting, an industry where you manufacture something and you scan every object that goes through your door, you might end up with quite a good training set for these large images. But most X-ray imaging is used if it's used in manufacture, it's often used in high-value manufacturing, say 3D printing, where you build objects that you have never built before, maybe use materials or process that they haven't used before. So getting good training sets is really problematic. So having enough training examples. And then the inverse problem which we want to solve. So we have all these measurements and we want to get images out, and we want to get rid of all these artifacts that we might get. It's very ill posed. So we need to have some more information. We can't just rely on our measurements unless we have enough measurements. And another point, the noise and artifacts aren't actually isotropic in X-ray imaging. So they all depend on the scan geometry and so on. So there are lots of issues which you probably don't have to the same extent in many standard imaging and machine learning problems for imaging. So in NXCT, things are a bit different. So, but what might we want to actually use XCT for? So these are the problems. But what do we actually want to solve, and why might we want to use machine learning in the first place? Now, as I said, images, the space of all images is massive. And often to regularize our inverse problem, what we really want to do is we want to look at a subset of the images. So we want to kind of find some structure, and we want to get images that have some useful structure. So that's perfect for machine learning. Can we use machine learning to learn typical image structure in an application domain? Whether it's, say, if you do 3D printing of metal components, or you look at cells and cell imaging, can you learn this structure of the typical cell image? If we look at a kind of spectral X-ray CT, where we have these X-ray spectra that we want to estimate, can we learn the structure of these spectra? Because the physics tells us there should be few parameters that define one of these spectra. So there's a lot of structure in these spectra. They're not just random. Again, can we learn that structure? Can we learn the structure of the noise? Once we've learned this structure, we have this inverse problems. Can we speed up the inverse problem using machine learning techniques? Can we reduce the data size, so we don't actually have to store all the data? Do we actually have to measure all the data? And then there's things like this scattering. We can simulate the X-ray scattering, but normally, one way of doing is just photon by photon simulate the scattering. But that's just physically, computationally impossible just to simulate on this physical level. So how do we kind of simulate these X-ray physical phenomena or to model the forward problem, in order then to solve the inverse problem that we might be interested in? All right, so the rest of the talk, I just want to give a few examples of things that we've done where we're trying to model some structure, in our high-dimensional data sets to kind of help us with some of these inverse problems. So let's kind of start by looking at a problem in X-ray spectral imaging. So the first problem, you might have, if you don't have one of these detectors that distinguish different energy levels, one way of doing it, you can take your X-ray source and you kind of crank up the voltage on them. And each time you change the voltage, you get a different shape, a different kind of energy profile for your X-rays that come out. So here are kind of on the kind of two different simulations of X-ray spectra that you might get out of an X-ray source. And we see, the different colors represent kind of different voltages. So the blue line on the left here is 50 kilo electron volt, which is the maximum energy. So you kind of see where the maximum energy is. You get out of this blue curve. That's kind of the voltage you set to on your X-ray source. So this one is set to, the X-ray source is set to 50 kilovolt. And the maximum energy photon you get out is 50 kilo electron volt. But most of them sit kind of around the 30 kilo electron volt, most of your X-rays. And then, you crack your energy up to 80, to 110, to 140, and you get different spectra out. And you see these peaks, which are kind of typical of certain X-ray sources. So if you don't have a way of actually measuring the spectrum with a detector that can resolve energies, one way that you could do is you could put different materials of different thicknesses in your X-ray beam and measure how much X-rays go through different materials. And that then might allow you to estimate what the source spectra is. If you do enough measurements, you might get an estimate of the source spectra. However, that is a very ill-posed problem. But as we see here, source spectra, they have this smooth curve, and then at certain energy levels, they have these spikes. Maybe we can learn this kind of structure and learn ways of estimating the source spectra from measurements or through objects. The next thing we might want to do is, now we've measured the source spectrum, now I put a new object into my scanner, and now I want to know how this, what's this object made out of? What materials are in there? At each point in this object, what's the absorption spectra? So the first thing was what we just looked at was the source spectra. So the energy dependent of the energy you get in your X-ray source. And now you want to know this part in space. how does it absorb different energies? So that's absorption spectra. And here's kind of just 4 examples from the NIST database. So the NIST database is a physics database which kind of lists your X-ray absorption. And again, we see these kind of specific features in here. These, what we call, again, these are K absorption edges. They depend on the material, but otherwise they kind of all look fairly similar, these absorption spectra. And I can now look at, what my X-ray source, what my spectrum would look like after going through a source and then going through a material. So that's kind of the spectra I get for, again, for the different source volumes, voltages going through different materials. So aluminium, iron, iodine, and lead. And we see, different kind of different shapes. Now, what we measure is not these spectra, we measure the average of these, if we don't have one of these fancy detectors. So how do we go from that to an estimate of what material is there, for example? So to show a bit about learning and this high dimensional structure. So here's kind of, what happens in an imaging example. So there's a simulated example, but you see the same thing with real data. So we have kind of an original image with different materials. So each gray level here is a different material in my image. And, we image this image just with a very few projections. And then the simulation of the data assumed that we had, this spectral, this energy spectrum. But when we reconstruct it here, the reconstruction algorithms, they just use the standard linear model. And, so filtered back projection, if you have very few projections, you don't actually get very good data out. But then, you might use iterative methods without regularization, but just running for a few iterations, or you use kind of standard regularization methods such as, wavelets, TV regularization, and Tim kind of pointed to some paper already kind of comparing, these type of methods. And you see, you get kind of improvements, and the best kind of signal to noise ratio we get here is kind of 9.3 with total variation reconstruction. And that's kind of well-known, good method. However, we know the model is wrong. It's not a linear model, there's this non-linearity. So if you actually take account of that model, we now get not just one image that we want to estimate. Now we get kind of an image dimension and we get an energy dimension. So if you have an energies, or what we call a polychromatic model, we basically have a matrix that we want to estimate, not just a vector. I think of images as vector, they just have a spatial dimension. Even if they have 3 spatial dimensions, I just take each voxel and then just make a long vector out of them. And now I have a kind of a second dimension with energy. And in this model, we can kind of use other models to regularize. So we can use, for example, what's called a non-negative matrix factorization on top of our wavelet. So in space, we want wavelets, which kind of try to make things smooth and spatially. But then if you think of the data as a kind of space by energy data set, we can kind of decompose that into a non-negative matrix factorization, where we have this one matrix, we decompose it into 2 smaller matrices, where one is a spatial kind of matrix and the second is kind of an energy matrix. So it's kind of a mixture of our data described as a mixture of different energy profiles. And we see, if we kind of have this kind of better model, this more accurate model, and we kind of regularize it correctly, even if we just image with one source energy, we get better reconstructions. Now, that's where machine learning can come in to further help us regularize things. So, typical energy spectra have a certain shape. So we can train, for example, an autoencoder. And here we just use our spectra and we just cut it into 20 energy bins rather than the 200 energy bins. And we trained a kind of an autoencoder where we have kind of our 20 energy bins going in, our 20 energy bins coming out, but we squeeze it through just 2 or 3 nodes. And we train it as a denoising autoencoder. So we see that, when you put a spectrum in, with noise on, you get this yellow line, you basically get very close to your original spectrum. What that really means is that, these X-ray spectra have very low dimensional representations. I can represent my X-ray spectra with just 2 or 3 parameters, even though they are 20 dimensional or 200 dimensional. just using 2 parameters or 3 parameters gives us good approximations of these spectra. And that's really useful because that really helps narrow down our search for good solutions to all of these problems. We can then use this autoencoder kind of in an iterative algorithm to reconstruct the images. And, this is just, to show that, so if each pixel on or voxel in our image just is a mixture of 3 different materials, so it's a mixture of 3 absorption spectra or 6 absorption spectra, and then we can, depending on what kind of network architecture we use, we get a different kind of quality results. The next thing then is, now I kind of not only have my spectra and I know which voxel in my image has spectra, different spectra, I can now also estimate what materials they are. So here are kind of the 92 materials. Don't know why it just goes to 91. That's, well, it's just off numbers here, I think. So 92 materials going up to uranium. We stop at uranium. First of all, we don't have data for absorption spectra above uranium. And if you're working with anything higher than uranium, you're on your own. Just once we've estimated the spectra, we can then estimate the materials within these pixels. So the estimates are here to the left and the true ones are to the right. And the estimates are actually shifted one element here just to visualize it better. So these are exactly nearly correctly identified, just the proportion of this material. I think it's element 52, whatever that is, versus element 3. So element 3 is slightly underestimated. Element 52 is slightly overestimated in terms of proportion or density. And then there's also element 2 is estimated rather than element 3. So a bit of element 2, because element 2, this absorption spectrum looks very similar to element 3, and it's difficult to distinguish. But, that's fairly successful. On the left, we kind of estimated element 77 fairly correctly, but the other elements aren't, we kind of made mistakes. But again, we make mistakes by picking similar elements.
2 minutes,
so this is
Thomas?
Experiment. Sorry, yeah?
2 minutes?
Yeah. I'll have a little clog at the top, which is hurrying me on already. So, we can use machine learning to learn these low-dimensional structures, for example, of energy spectra. But there are lots of other low-dimensional models we might want to use. So in imaging, we often use voxel representations, so they're square little boxes. What we've done is we use mesh representations. So the advantage of mesh representations is that we can have changing density through the material. We can use additional information, such as aligning cut data with our model. And then, so we instead of working with voxels, we directly working with a mesh. So all the back reconstruction and it's all done directly into a mesh. And we are also able to kind of refine our mesh iteratively. While doing reconstructions, we start with a really rough mesh. And then where we need to refine the mesh, we automatically refine the mesh. So this is a kind of just the mesh on just a slice through the mesh of an image sphere. So the first estimate of the you kind of see the boundary of the sphere here. There's something round here, and then that's kind of the mesh, which starts to look a bit random because we randomly refine it, well, randomly data-drivenly refine it. And the more we refine it, the finer and finer we get around the surface of the mesh. And one of the reasons we're doing that is because we want to use, any prior information that we have. So in industry, when you build an object, you know what material or what shape you're looking at. You know what material you're looking at as well. So can you use this cut data to help you in the reconstruction? Now, this example, before I end, is looks at using this kind of cut data, and this is a machine learning example, not on the mesh. This is actually on voxels, but so what we have is we have kind of, this is the Sophia Beats data set. We kind of seen that earlier already, come out of Manchester, quite nice data set. What we've done is we kind of identified where all the little spheres are in the image. So the image down here is kind of known shape. So we know there are different objects that have roughly that shape, but we don't know what the attenuation is. And then we do X-ray measurements, and we just measure, if we would get all the projections that we need, that would be 100%. But we're interested in difficult problems. So let's say we just image 5% of the data. So we, instead of taking 3,000 projections, we're taking 5% of 3,000, how many ever that is. And if I just do filtered back projection, that's the image I get out. It's not a good image down here. 5%, you don't get any useful information out unless you use additional information. So this is our machine learning reconstruction up here, where we use this kind of shape information in addition to our projection. So we know roughly where the spheres are. Not all spheres are represented in our data. So this sphere, I think here is, for example, is missing in this data, or this sphere here is missing. So there are a few small spheres that are missing. We also haven't identified the container, which you kind of see out on the outside here. And we don't really get the container back, but we do get certain missing spheres back. So that's just zoomed in. All right, so just acknowledge some of the funding that kind of enabled that work, and I think I leave it here.